Hello and welcome to this Bits of Q series on template metaprogramming in C++. I am your host, Quirijn Bouts. Let's get coding. In the previous episode, we created our first algorithm as a metafunction. Specifically, we created this contains type metafunction that allowed us to check whether a certain type was present in a tuple. To write this metafunction, we relied heavily on the infrastructure around the standard tuple. In particular, the std tuple element t. We use this function to retrieve the type of an element at a given index. Now obviously, we don't want to use tuples for all our future metafunctions. So in this episode, we'll look at how to create our own container of types. And to ensure that our container can take an arbitrary number of types, just like the standard tuple, we will be using what's called Variadic templates. Let me explain what they are by writing a function that uses them. In episode 1, we used templates to create a function, print3, which printed 3 arbitrary inputs separated by commas. In this episode, we will write a printn function, which can accept an arbitrary number of parameters, and again will output them separated by commas. We should, for example, be able to use our printn function to print this combination of integer, a const string, a double, and a boolean. Now, as we discussed in the previous episode, we don't really have for loops or while loops when doing template metaprogramming. So we will again have to rely on recursion for this function. So we'll define our first input to be of type name t0. And now we'll use this triple dot syntax, the ellipsis, to indicate that there can be an arbitrary number of type names following. For the signature of our function, you'll have a little t, which is an instance of type t0. And now we again use this triple dot syntax to specify that it's followed by rest, which is a so-called parameter pack. And it is of the types that are identified by the Variadic template parameter t1 to n. Now we output our little t followed by a comma, and then we want to output the rest of our template parameters. So what we'll do is we'll recurse, and now we again use this ellipsis to expand the parameter pack rest. What that means is that all the different parameters that the compiler figured out were needed for the instantiation of this function will be passed to printn. So we are using this ellipsis symbols in 3 different ways here. In the declaration of our template parameters, we see that we have the ellipsis in front of a name. If you see an ellipsis in front of a name, then it is a declaration of a variable number of elements, in this case type names. By putting the triple dot after our parameter pack, we are expanding it to a list of all the elements it represents. In this case, the remaining arguments to our printn function. Lastly, we use ellipsis in between 2 names to define that the second name, rest, is a list of parameters given by the first. Now we see we get an error here. No matching call for printn. That's because as we recurse at some point we run out of parameters, and then we try to call printn without any parameters. And clearly there's no overload that would match. So what we'll do, we'll create another template, printn, taking a single template parameter, specifying the type of the last element passed to our printn. In this case, we'll just print this t and also add a new line. Now, strangely enough, it seems that this did not solve our problem. The compiler is still complaining that it cannot find a printn taking no parameters. The reason for this is that when the compiler gets to this line where we want to recurse, it does its overload resolution in the context of the template instantiation. What that means is that it's looking for overloads that would fit the parameters that it has available. But when doing this, only those overloads that are visible at this particular point are considered. And since our println last overload is specified later, the compiler doesn't see this, and as such has no other choice than to continue using the same println function. Luckily, we can easily fix this by simply moving the println last overload to be declared before our main println function. And now we see that we get the correct output. Now there's still one corner case that we should take care of, and that is the situation where we call println without any arguments. So let's define one last overload to also deal with this case. Now let's write another function, this time to print a tuple. So I will use std make tuple here to define our tuple, and I will just pass it the same set of parameters. So this is defining a tuple of int pointed to const char, double, and boolean. And I want to be able to just print this tuple using a print tuple function. So we'll again create a template with a single template parameter, namely the tuple type name. And now we're going to use a bit of a trick here. We will call an implementation function, print tuple impl, with our tuple, but also with a second parameter, a so-called index sequence. With std make index sequence, we can define an index sequence for numbers 0, 1, 2, 3, up till the size that we pass, in this case the size of our tuple. I can now define this print tuple impl to be a template taking one type name parameter and then an arbitrary number of size t's, our indices. As for our parameters, we can take this tuple and then we'll take an instance of std index sequence with this particular set of indices. Now I'm not going to name this parameter to our print tuple impl because we will not be using it. The only reason it's here is so the compiler knows which overload to pick. This principle of taking a parameter just for the type and not for its data is called tag dispatch. Now our implementation function will just call our println function that we defined before, and it will call this on all of the elements in our tuple. We'll do this using stget, passing it the indices, and then our tuple t. And now, here's the important part. We will expand this parameter pack after the closing parentheses. So what's happening now is that the compiler will just generate enough copies of this stget statement so it can execute it with each of these index parameters. So essentially we'll have a println of stget0 of t, stget1 of t, stget2 of t, etc. And as you can see, our print tuple function now works correctly. It outputs 9, hello, 1.5, true. So this in a nutshell is how you can use Variadic templates to deal with an arbitrary number of parameters or types. Now, while writing this code, I want to keep things as simple as possible, so I've been passing everything by value. Now, in contrast to the previous episodes where everything was handled at compile time, here we are actually passing data around. And since we take our parameters by value, that means that we'll be making a lot of unnecessary copies. And this is really going to hurt your performance, especially if your inputs are expensive to copy, such as big strings. The best way to more efficiently pass your inputs is to use perfect forwarding. Now, I don't really want to explain perfect forwarding in detail here, but I do want to quickly demonstrate what this would look like. If you never worked with perfect forwarding before, this will probably be a bit hard to follow. I will leave a link in the description with a good introduction in case you're interested. But feel free to just skip the next 2 minutes, as this is not that important to the metaprogramming we'll do in the next episodes. So we'll change our signature to accept our tuple as a forwarding reference, and then we'll use std_forward to pass it to the impl function. Now, for our index sequence, we see that we get an error here, and that is because we cannot use tuple size on a reference, only on a tuple. So we can use a little meta function from the standard library, std_remove_reference_t, to change this template parameter, which is a forwarding reference to a tuple, to just a normal tuple, allowing us to call tuple size on it again. And now this should work for both normal tuples as well as const tuples. Next step, updating our print tuple impl. Again, we take our tuple as a forwarding reference and we forward it using std_forward. Note that I'm not changing our index sequence parameter because this type doesn't contain any data, and as such is very cheap to move around. I expect that the compiler would even optimize it out in this case. We do the same thing for print n, accepting our inputs as forwarding references. And now to correctly forward our parameter pack rest, we use std_forward on our t1 to n, pass it to the parameter pack, and now again, only after the closing parenthesis, we'll use this ellipsis to expand the parameter pack. So essentially, what this expands to is print n of std_forward, your first type, call it t1, and then the first argument in our parameter pack, say rest1, comma std_forward t2 rest2, etc. Lastly, we have the printn function with a single template parameter, again taking it as a forwarding reference and using std_forward to pass it into our cout. So, in summary, we have seen how we can use Variadic templates to deal with an arbitrary number of inputs. We have used recursion to operate on these inputs one by one, and we have seen how we can combine an std_index sequence with parameter pack expansion to execute a function on each of the elements in the tuple. That's it for this episode. I hope you enjoyed it and learned something new. If you did, make sure to leave a like and consider subscribing to the channel. See you next time.